Okay, welcome to the Unit 3, Lesson 2. This is Quadratic Systems Part 2. So we'll be looking at solving systems with circles. Alright, so the first set of problems that we're going to look at here involve linear and circular systems. So where one equation is a circle and one equation is a line. So in these types of situations, the possible number of solutions will be 0 solutions, 1 point of intersection, or 2 solutions. Remember that solutions are coordinate points. So you always want to write it in an XY, where the graphs will intersect. Alright, so first set of problems here we'll look at involve diagrams, right? Where we'll show you the graphs and you want to pick out the apparent solutions. And apparent, when we say apparent solutions, we're just talking about the ones that you can see, like trust your eyes. So we have a solution right here. We have a solution right here. So again, we'll pick this bottom one here, which has an x coordinate of 3 and a y value of -4. So we'll say 3, -4. And we'll say here, we'll say 6, 5. So this one has 2 solutions, 3, -4, and 6, 5. And our second diagram here, we're going to go with apparent. So I only see 1 point of intersection here. So in this case, this is called a tangent line. Now you don't need to know that yet, but we'll get to that later on, but just to kind of introduce it, it's a tangent when a line touches a circle on 1 point. It's called a tangent. One intersection, and that coordinate plane or coordinate point is -2, 0. All right, and our third here, there are no solutions, no real solutions. Now there could be some imaginary solutions going on, but again, we're not going to worry about that in this situation. We'll just say that there's no solutions, no real solutions to this equation, to this system, and we'll move on from there. So, if we are to algebraically solve a linear or circular system, we'll use substitution in most cases. So, if it's not already set up for one variable, then we'll solve for one variable. So we'll say y will equal 4 minus x. So I just brought the x over to the other side. We'll say y equals y equals 4 minus x. Alright, so we're going to substitute this, right? We're going to take this equation, or this expression, we're going to substitute it in here to the first equation wherever we had a y. Alright, so we'll start off with x squared plus, and then we'll throw a little parentheses in here, and we'll say 4 minus x. Close that off. We'll square it, and then we'll set it equal to 16. Alright, so then from here we'll simplify. We can do 4 minus x squared. So this will give me x squared plus 16 minus 8x plus x squared equals 16. And if you're not sure how I foiled this 4 minus x squared, then you should work on squaring binomials and how to quickly do that without having to completely distribute. But if you have to completely distribute, you can. So we'll combine our like terms here, and we'll get 2x squared minus 8x plus 16 equals 16. So if I was to get this equal to 0, I would subtract the 16 from here, and that ends up giving me 2x squared minus 8x equals 0. So from here I can factor. So I'm going to take a GCF of 2x out. That leaves me with x minus 4 equals 0. So I have x equals 0, and I have x equals 4. So from that situation, I can go back up to this equation, right? And I'm just going to bring that all the way down here. and we'll plug that in. So we'll say y is equal to 4 minus 0. So in that case, I get the coordinate points 0, comma 4. And we can also say y equals 4 minus 4. And that would give me the second coordinate point of 4, comma 0. So there are two solutions to this system, and here are both solutions. So we can go ahead and try this again. In this case, the y is already solved for x. So, and it doesn't matter which way you do this. So this time I'm going to plug y into the x, right? So I'll say parentheses y squared plus y squared equals 8. So that gives me 2y squared equals 8. Divide them both by 2, and I get y squared equals 4. So y is equal to plus minus, right, the square root of 4, which is 2, because I'm going to take the square root of both. So that will give me here. So again, that is two solutions. So I'm going to plug that back into my original equation, y equals x. So I'll say 2 equals x, which means that my first point is 2, comma 2. And I'll plug it in, the negative 2 equals x. So that gives me negative 2, comma negative 2. So again, there's two solutions to this system as well. But there's no guarantee that there'll be two solutions. There could be one, there could be 0. So just make sure when you're taking the square root of both sides that you're getting a positive negative, and that you count that as two separate y values. Plug them into the original equation, y equals x, to get your x values, to get your two solutions. Alright, so try the next one here. But before you pause the video, let's make this a little bit different. Let's make that, just get rid of the 3, and let's make this a positive 4. So the equation you're going to work with is 2x minus y equals positive 4. Alright, so solve for y there, and that's going to make this problem much easier than what it was harder than I intended it to be. So let's switch this second equation to 2x minus y equals 4, and then pause the video, attempt this problem, and then we'll come back and check it. Alright, so pause the video. Okay, so your solution to this should be 1/5 and negative 18 over 5, and the point negative 3, negative 10. So go ahead and look through the work that I did here if you didn't get those solutions, and see if you can find where you made a mistake or where I made a mistake if our answers aren't the same. Otherwise, you should be able to get those solutions with substitution. Alright, so we'll move on to the next topic here, which is quadratic circular systems. So again, we're going to be looking at graphs here and the possible number of solutions with a circle and a quadratic function would be 0, 1, 2, 3, or 4. Alright, so those are the possible number of solutions we can have when two curves intersect. So if we're looking here at this first graph, we see a point of intersection here, here, and here. So we have solutions, right? At this point, it's a little bit difficult to see, but on your paper, you should be able to see that it's at negative 7, comma 4. This one, we have negative 1, comma 4. And down here, you should have the solution of negative 4, comma negative 5. Alright, so over here we have solutions right here and right here. So you should be able to tell me negative 3, negative 4. You should be able to tell me negative 1 and 4. So you kind of, and here we see that there are no solutions, no real solutions. So you should be able to find the solutions for these two graphs and tell me what they are. So go ahead and pause the video, check and see what the solutions are, and then come back. Okay, so you should have these solutions here of -8, 4, 4, 4, -4, -4, and 0, -4 for this particular graph. And for the last one here, just one solution of -2, -5. So again, you should be able to identify points of intersections when quadratics intersect with circles, identify how many solutions there are based on the graphs. Remember, solutions to systems they occur where the two graphs intersect each other, not where they intersect the y-intercept. So again, we're going to look at how to deal with this algebraically. So very similar to what we did with the linear, we're going to solve for one variable and substitute it in. Now here, it's important which variable you're going to substitute it in, because what we want to do is try and get rid of this x squared. So instead of an x squared, I'm going to plug in a y. And what's nice about that is this equation x squared plus y squared equals 20 becomes y equals y plus y squared equals 20. So if I write that in standard form, I get y squared plus y minus 20 equals 0. So factors of 20 that subtract to give me 1. That'll give me y squared plus 5y minus 4y minus 20 equals 0. So when I factor that out, I get y plus 5, and I get y minus 4 equals 0. So my y solutions are -5 and y equals +4. We're going to plug that back up in there and see y equals x squared. So if I said x squared equals -5, so if I take the square root of both of those, I see that I get x equals plus minus I root 5. So that is not a real solution. So systems, we want real solutions, so we're not going to worry about this imaginary solution, because on the graph they would not be crossing at that coordinate point. So then we'll stick it over here and we'll say x equals 4, x squared equals 4. So again, we'll take the square root of both sides and we get x equals plus minus 2. So that gives me 2, 4, and the point -2, 4. And so I see that this system has two solutions, one at 2, 4, and one at -2, 4. So again, example 2 is a little bit kind of ridiculous, hard. If you would like to try it, by all means, give it a try, but it's a little harder than it was intended to be. It probably works much easier if we use a +4, but if you want to try it, go ahead. We're going to skip it, and I would say give number 2 a try. Again, we want to isolate for x squared, and if you do that, you bring the x squared over and you bring the 3y over, you get something that looks like this. So let's substitute that in for x squared, solve for y, and then try to find the solutions to that system. And I'll give you a few minutes to do that. So pause the video while you work that out, and then I'll come back and kind of talk through the solutions and show you what you should have. Alright, so pause the video. Okay, so again, when you work that out and you substitute it in, you should end up with y equals 6 and y equals -3. However, when I plug my 6 into my equation, I end up with imaginary solutions again, which are not points of intersection on the graph. So again, I'm not going to focus on those. I'm just going to cross those out. And when I plug in my other y value of -3, I end up with x squared equals 11. So I get plus minus square root 11, which gives me my 2 points of intersection, -3, comma, positive square root 11, and -3, comma, negative square root of 11. So 2 solutions to this system. and there would be 2 points of intersection. So again, you should be able to get to the solutions that I found. If you have any trouble, look back at the work I did, and if not, then we should be good to go with the classwork next time in class. So come with any questions or problems you had with this, and we'll talk through it in class. All right, have a good day.